Hello, welcome to my channel RD Physics. I am Dr. Rashmi Deshpande and this is a course on atomic and molecular physics. This is 6th lecture of the series. Today we are going to study the orbital angular momentum quantization in magnitude and direction. Let us first see the interaction between orbital magnetic moment and external magnetic field. When an atom is placed in an external magnetic field P bar, the magnetic dipole has an amount of potential energy Vn, which depends upon the magnitude of magnetic moment and orientation of this moment with respect to the field. See, here we are considering the atom as a magnetic dipole, and this magnetic dipole, when placed in an external magnetic field B bar, how the interaction between the dipole moment, that is the atomic dipole moment, and the applied magnetic field, how the interaction affects the potential energy, or how it gives rise to the increase in the potential energy of the magnetic dipole, that we are going to see. So the torque tau, which acts on the dipole, is given by cross product of the magnetic moment, that is the cross product of dipole moment and the applied magnetic field. So vector tau is equal to cross product of vector mu and vector b, where b bar is the applied external magnetic field. So in magnitude we can write that tau is equal to mu b sine theta, where theta is the angle between the magnetic moment and the applied magnetic field. This torque tau is maximum when the dipole is perpendicular to the field, because sine theta is equal to 1 for theta equal to 90 degrees, and this torque is 0 when it is parallel or anti-parallel to the field, because in that case theta will be 0 and so sine theta will also be equal to 0. This torque tries to displace the dipole with respect to the magnetic field, and this gives rise to the potential energy Vm, which is the external work done in bringing the dipole mu bar from a reference orientation theta 0, where we consider that Vm is equal to 0, to the orientation theta. Let this reference position theta 0 is equal to 90 degrees. So Vm will be equal to integration tau d theta. This is just like we calculate work done or potential in case of linear motion. It is product of force and the displacement. Similarly, here we are considering there is a small angular displacement of the dipole, that is through a very small angle, and it is the angular displacement, it is caused by the torque tau. So therefore the work done in bringing the dipole from the reference position to the position theta will be stored as magnetic potential energy, which is given by integration 90 degrees to theta of tau d theta. So substituting the magnitude of vector tau, which is we have seen in the last slide, which is equal to mu b sine theta. So we have substituted that, and because mu and b, that is the dipole moment and the applied magnetic field, these are constant with respect to the variable theta, because they do not depend upon theta, so therefore they will be out of the integration sign, and mu b integration sine theta d theta. If we substitute the limits of integration, then because integration of sine theta is minus cos theta, what we will get? Mu b, that is minus mu b cos theta upper limit is equal to theta, lower limit is equal to 90 degrees, where cos of 90 degrees will be equal to 0. So just Vm is equal to minus mu b cos theta. This is equation number 10 which we have obtained, and we can write it as a dot product because minus mu b cos theta is nothing but minus mu dot b. We are using here suffix L for the magnetic moment because it is the orbital magnetic moment, and for orbital motion we are using the suffix L. Therefore, at theta equal to 0, that is when mu bar and b bar are parallel, Vm is equal to minus mu b, which is minimum value of Vm, and the magnetic dipole therefore tends to align itself with the applied magnetic field, because any system will try to be in the state of minimum energy position. So therefore this is the most favorable position of the magnetic dipole. So magnetic dipole will tend to align itself with the applied magnetic field, and in this process the magnetic dipole will precess about the direction of the applied magnetic field. How that we are going to see in the next slide. Now because this Vm is equal to minus mu b cos theta, so we know that mu, that is the magnetic moment, and the orbital angular momentum L, these two vectors are oppositely directed with respect to each other, and mu is equal to minus E upon 2m into L bar. So in vector notation, mu bar is minus E upon 2m into L bar, that we have seen in the previous lecture. So if we substitute for mu in terms of the orbital angular momentum L, then this Vm is equal to E upon 2m L into b into cos theta, where theta is now angle between orbital angular momentum vector L bar and the applied magnetic field B bar, because mu bar and L bar both are oppositely directed. So therefore whatever is the angle between mu bar and B bar, same will be the angle between L bar and B bar. So we can write this particular equation in vector notation as the dot product Vm is equal to E upon 2m L bar dot B bar. I can also write this particular equation number 12 as Vm is equal to E upon 2m B into L cos theta. What is L cos theta? This is nothing but component of L bar along vector B bar, and we denote this component of vector L bar along B bar as Lz if we take B bar to be along Z axis. So Vm is equal to E upon 2m into B into Lz. Now we are going to see how Lz, that is the Z component of L bar vector, is quantized, and how that leads to space quantization. Let us consider the direction of external magnetic field is along Z axis. Now what is the Z component of orbital angular momentum? This we can obtain by operating the wave function of electron in hydrogen atom with Lz operator, because we know that if we want to determine the value of a physical quantity, we can use the corresponding operator. So Lz operator in spherical polar coordinate system is written as minus I h cross del by del phi. The wave function of electron in hydrogen atom, that is psi, which is a product of r, theta and phi, we are going to operate this wave function with the Lz operator. So it is written over here in this particular expression. Okay, the wave function psi is operated with Lz operator. Now in the product r, theta, phi, we can see that the partial derivative of phi function only can be calculated. R and theta will be treated as constants because they do not contain the variable phi. So r and theta are taken out of the derivative operator. So it is Lz operator operating on psi wave function is equal to minus I h cross r into theta into partial derivative of function phi with respect to variable phi. But we know that the phi function can be written as a, that is normalization constant, into exponential I ml phi. Remember, this ml is nothing but the magnetic quantum number m suffix l. So the partial derivative with respect to phi will be, this a will remain as it is. Derivative of e raised to I ml phi is equal to I ml into e raised to I ml phi as it is. Okay, so this is nothing but again the function phi. Okay, so it is I ml into phi. So Lz operating on wave function psi gives us minus I h cross r into theta as it is, multiplied by this partial derivative which is equal to I ml phi. So r theta into phi is nothing but psi, minus I into this plus I is equal to plus 1 and h cross as it is. So ml h cross psi is the result of Lz operator operating on psi. So ml cross is eigenvalue of the operator Lz from the definition of eigenvalues. So therefore the value of Lz, that is the Lz component, is equal to ml cross. But we know that Lz is equal to L cos theta, that is the component of L bar vector in the direction of z axis, that is in the direction of applied magnetic field. So L cos theta is mlh cross. So cos theta is Lz divided by L. What is Lz? It is mlh cross in the numerator divided by L. What is L? Magnitude of L vector is h cross under root small l into L plus 1, where small l is the orbital quantum number. Cancelling h cross from numerator and denominator, we get this ml upon under root of L into L plus 1, that is cos theta. So cos theta can take up 2L plus 1 values, because you can see ml can take 2L plus 1 values. That means theta can take 2L plus 1 values. So cos theta has these many values, and so with respect to a fixed z direction, which is the direction of magnetic field, the angular momentum vector L bar has 2L plus 1 possible orientations, because cos theta has got 2L plus 1 values. That means theta has 2L plus 1 values. 2L plus 1 values. That means L bar has 2L plus 1 orientations, possible orientations with respect to the applied magnetic field. This shows that not only magnitude but direction of angular momentum is also quantized with respect to an external magnetic field. This is called as space quantization of orbital angular momentum. That is because of these 2L plus 1 possible orientations, the space is divided, okay, because of the different orientations of the orbital angular momentum with respect to the applied magnetic field. It is like the division of space into different parts. So it will be clear from the diagram which we are going to see in the following slides. Okay. Now can L bar be exactly aligned parallel or anti-parallel to B bar? The answer is no. This is because then Lz will be equal to L. Okay. If B bar and L bar are in the same direction, then Lz will be equal to L. But we have seen that Lz is equal to mlh cross, and L is equal to, means magnitude of vector L is h cross into root of L into L plus 1, and mlh cross is always less than this. mlh cross is always less than the magnitude of vector L bar. So therefore L bar vector can never be equal to, can never be aligned parallel or anti-parallel to B bar. So the vector top tries to align vector L in the direction of B bar, but it is never possible to align L bar in the direction of B bar, and in the process there is a precessional motion of L bar vector with respect to the direction of B bar vector. So L bar is precessing around the direction of B bar and it traces out a cone. Okay, it traces out a cone around the direction of B bar. So when an atom is placed in a magnetic field, its orbital angular momentum assumes a certain orientation corresponding to a certain value of ml. Please see that because theta is constant, for this orientation of L bar vector, Lz will be constant, but the direction of L bar is constantly precessing, constantly it is changing around the B bar vector. In the absence of an external magnetic field, the direction of z-axis is arbitrary. Hence, the component of L bar in any direction we choose is MLH cross. Thus, an external magnetic field provides an experimentally meaningful reference direction for the measurement of Lz. Okay, because when the magnetic field was not applied, there is no reference direction. So we can take our z-axis in any direction. Okay, and so the component of L bar in any direction that we have chosen will be equal to MLH cross. Okay, so this particular space quantization concept of orbital angular momentum vector, this arises only in the presence of magnetic field. In figure A, we can see that there is an example. We are considering that the atom is in p state, so that L is equal to 2. The orbital quantum number L is 2 for a p state electron. Okay, and so ml will have values 0, +1, +2, -1, -2, and correspondingly we can see here Lz will have values 0, +h cross, 2h cross, -h cross, -2h cross. For all these orientations, we can see that the magnitude of orbital angular momentum vector is constant, that is √6h cross. Okay, but these are different orientations of L bar vector with respect to the applied magnetic field, which give rise to different values for Lz. Okay. So now the question arises, are all three components of orbital angular momentum quantized? Means along with Lz, can we say that Lx and Ly are also simultaneously quantized? The answer is no. Only one component of L bar is quantized. This is because direction of L bar is not fixed, as we have seen in the previous diagram that L bar is precessing about the direction of B bar. It traces out a cone in space such that its projection Lz is MLH cross. Okay, and the reason why Lx and Ly cannot be simultaneously quantized, the reason is Heisenberg's uncertainty principle. Suppose if all the three components Lx, Ly and Lz are fixed, then what will happen? We know that the plane of orbit of the electron will be fixed. If Lx, Ly and Lz are fixed, means L bar vector is fixed. If L bar is fixed, because L bar is perpendicular to the plane of the orbit of the electron, so if L bar is fixed, plane of the orbit of electron is also fixed. We consider an example where, say, L bar is in the z direction, that is along z axis. Then in that case, Lx will be 0, also Ly will be 0. Okay, this is shown in this particular diagram. See, L bar vector is along z axis. So the orbit of the electron is in the xy plane. The z coordinate of the electron will be 0 because the electron is moving in xy plane, and so pz, that is the corresponding linear momentum, will also be infinitely uncertain. Okay, if the z coordinate of the electron is 0, this will make delta pz infinite. Why? Because Heisenberg's uncertainty principle states that delta z into delta pz should be greater than or equal to h cross. And if delta z is equal to 0, if z coordinate is 0, then delta z will be 0. And so delta pz will be infinite. This is impossible. That means uncertainty in the measurement of pz is infinite, that is impossible. So in reality, only one component Lz and magnitude L have definite values, that means they are quantized, such that mod of L is always greater than or equal to mod of Lz. That means magnitude of vector L is always greater than magnitude of Lz. The electron is not limited to a single plane, and there is a built-in uncertainty. The direction of L bar is constantly changing, such that the vector L bar is precessing, having a precessional motion like a top around the direction of B bar, that is the direction of applied magnetic field. This is depicted in the diagram. Again, we are considering the same case where the electron is in p state. We can see here in 3 dimension how it will look like if the L bar vector is precessing around the direction of the applied magnetic field. You can see that the precessional motion gives the precessional motion, because of the precessional motion, the tip of the L bar vector traces out a circle around the direction of B bar vector. If we draw a projection on z axis, this will give us the Lz component. Okay, we can see that the value of Lz is changing if the orientation of L bar vector is changing. And you can see here how the space is divided because of different orientations of the L bar vector, and that is nothing but the space quantization. And because this L bar vector is constantly precessing, therefore we can say that Lx and Ly, they are indeterminate. We cannot fix Lx and Ly, but only Lz will be quantized. Okay, so that was space quantization of orbital angular momentum. Thank you very much for patient listening.